Hi, this lesson is about tangent lines and velocity. But first, let's talk about lines, just some general information that you should know about lines. So the equation of a line in the form y equals mx plus b is called the slope-intercept form of a line. When your line's in that form, you can get a lot of great information about it. You have m, which is the slope, which is a measurement of the inclination or the slant of a line. And the b represents a point. The point 0p b is called the y-intercept of the line. We also know how to compute the slope of a line. As long as you know 2 points, it's going to be the change in y over the change in x. You might also know this as rise over run. So that's an important formula to know. And then you have something called the point slope formula, which is used to find the equation of a line. As long as you know the slope and the point of one point on a line, you can find the equation by plugging it into the point slope formula. So let's talk a little bit about the characteristics of a line when you know the slope of a line. So here are different scenarios for slope. So when your slope is positive, m is greater than 0, you can express your line in this slope-intercept form, y equals mx plus b. And the equation of a line like that will be a line that increases from left to right, so the graph will look something like what you see here. When your slope is negative, you can still express it in slope-intercept form, but this time the graph of it will decrease from left to right, so it will look more like this. Then you have the scenario where your slope is 0. When your slope is 0, that means that this term here, mx, goes away, so your equation is expressed as y equals b, so where b is a constant, and that graph is going to be a horizontal line, like what you see here. And then finally, you have the scenario where your slope is undefined, and when your slope is undefined, it cannot be expressed in this slope-intercept form because slope basically does not exist, is undefined. And so those lines are expressed in the format of x equal to a, where a is a constant. The graph of it will be a vertical line. So vertical lines look like this. Okay, so the information in this chart is important for you to remember. Okay, so let's relate this to lines with relationship to a graph. So we have something called a secant line and something called a tangent line. So a secant line to a curve is a line that intersects the curve at least 2 points. And in comparison, a tangent line to a curve is a line that intersects a curve at one point where the tangent line and the curve are actually going in the same direction. And remember, with graphs, you always read them from left to right the same way you read text. So here I have a curve. The curve is in this magenta kind of color, f of x. And I have 3 lines associated with this curve. I have line A in blue, line B in green, and line C in orange. So according to the definitions I just gave, line A is considered to be a secant line because it intersects the curve f of x at these 2 points that you see here. So that definitely satisfies the definition of a secant line. Then I have line B, which is here in green. That one satisfies the definition of a tangent line because it intersects f of x at a single point, and f of x is increasing at that point, and your tangent line is also increasing and going in the same direction as f of x. And then we have line C. Well, line C is neither a secant line nor a tangent line because it intersects the graph at only 1 point. But at that point, your graph of f of x is going downward from left to right, but your line is going upward. So therefore, the line, although it only intersects it at a single point, it doesn't go in the same direction as f of x. So it doesn't satisfy either the secant line nor the tangent line definition. Okay, so here we're given a parabola, y equals x squared, and we want to find first we want to find the slope of the secant line through the points of the graph that go through -2, 4 and the graph at 1, 1. So since it's intersecting the graph of x squared at 2 points, this is definitely a secant line. And in order to compute the slope, we need to know the y values. Now, in order to find the y values, you're just going to pick that out directly from the given points. So we have 4 and 1. So that's those are the two numbers that you need to subtract. So it's 1 minus 4 divided by the difference in your x values, which are the -2 and the 1. So it's 1 minus -2. And if you do that computation, it's -3/3, which is -1. You could have also done them in the opposite order, 4 minus 1 over -2 minus 1, which is again, works out to be -1. So either order is acceptable. So that's the slope of your secant line. Now we want to estimate the slope of the tangent line at the point -2, 4. So in order to compute the slope of a line, you need 2 points. So if I'm only given a single point, well, that makes it a little kind of impossible to use the slope formula. So we're going to estimate it by picking values that are very close to -2, 4, so that we could compute the slope of the tangent line, or at least guess what it would be. So here I have a chart to show you that I'm picking values close to -2, both less than -2 and greater than -2. So the top half of this chart have the values less than -2 that get progressively closer to -2. So I start at -2.5, -2.1 is even closer, and -2.001 is even closer. So I get progressively closer. I get the y values by plugging them into my function. And remember, your function is x squared. So -2.5 squared is 6.25, -2.1 squared is 4.41, and -2.001 is 4.004. Notice that these y values are also getting closer to what that y value is, the -2, 4. And then how do I compute my slope? Well, remember, it's change in y over change in x. So let me just put in what numbers you're using in order to compute that slope. So you're using the value that you're interested in. I want the slope of the tangent line at that point, and then this would be your second point. So I have 6.25 minus 4, that's the change in y, over -2.5 minus -2, and that gives you the value of -4.5. Then you repeat the process for the second computation and the third, and remember, you're always using the -2, 4 as your second point, and the other point would be, or your first point and the other point would be what you see here. So you can see that as I'm computing the slope of my tangent line, it goes from -4.5 to -4 to -4.1 to -4. Okay, then I do the same thing to the right of -2. So I need to pick values greater than -2. So I start with -1.5 and I get to -1.999. So I put the closest numbers next to each other, these two being the closest numbers to -2. I square each of these numbers and I get these y values. And then again, I compute my slope by plugging into the slope formula using -2, 4 as one of the points, and then these as my secondary points. So if I show you the work for this one, so my slope here would be -3.5 minus 4, that's the change in y, over, I'm sorry, I picked the wrong number, change in y, it would be 2 2.25 minus 4 over negative 1.5 minus 2. So that's again your delta y over your delta x, with this being the other point. And when you compute that, you get negative 3.5 as your slope there. When you repeat the process, you go from negative 3.5 to negative 3.9 and then to negative 4. So you can estimate that the slope, when you get really close to the point you're interested in, is negative 4, which is the conclusion that we draw here based on the table of values. The closer the values of x get to negative 2, from the left side of negative 2, and again, this being the left side, and from the right side, and this being the right side, then the slope value is converging to negative 4. So that's a good estimate. Then if I'm asked to find the equation of the tangent line to the curve at negative 2, 4, well, now I know what my slope is. My slope is negative 4, and I have a point. So you plug it into your point slope formula. So I have y minus 4 equals negative 4 times x minus negative 2. And if you solve it, you get, for y, you get y equals negative 4x minus 4. Okay, so all of those skills will be something you'll apply when you're doing the homework for this section. Okay, so applying what we just talked about to velocity, we have something called average velocity and instantaneous velocity. So computing average velocity is the same as computing the slope of a secant line, because an average implies that it's a velocity over two different time periods. So we have average velocity is the change in position divided by a change in time or elapsed time. If we let s of t be the position function, your average velocity would be your change in s over your change in t. So I actually wrote it here. This is your displacement or your position function. Instantaneous velocity, so the thought process here is for you to think of instantaneous velocity similar to computing the slope of a tangent line. So in other words, what's your velocity at a single moment of time or at a single point on your trip? So instantaneous velocity of an object relates to the slope of a tangent line at a particular point to a curve if it represents the velocity of an object at a particular moment of time or a single instant of time. So that's the same as computing the limit of delta s over delta t as the change in time approaches 0. So when your time interval approaches 0, meaning a single moment of time. So the notation for that would be what you see here. The limit as the change in time approaches 0. In other words, change in time is no change, a single moment. And then delta s over delta t is your slope computation. So these, for now, have to be done similar to the way we did the problem above, where you're using a table of values in order for you to estimate what that instantaneous velocity would be. So here's an example. So we have a ball is thrown in the air with a height defined to be s of t equal to 40t minus 16t squared in feet at time t in seconds. And we want to find, in part A, we want to find the average velocity for the time period starting at 2 seconds and lasting 0.1 seconds. So that means that your time is going to be from 2 to 2.1. Okay, so those would be the two t values. So that's what you have to subtract in the denominator. It's change in t. And your numerator is change in position. So in other words, what's your position at 2.1 minus what's your position at 2? And the way you figure out those values, well, you plug them in here. Remember, that's your function. It's a quadratic function. So when you do all those computations, you end up with a change in the position of negative 2.56 divided by zero point 0.1. And so that works out to be negative 25 feet per second. So that's your velocity over that 0.1 seconds of time, average velocity. So now we're going to make that same computation as t goes from 2 and elapsing 0.01 seconds. So in other words, my time interval is even shorter. So it's 1/100th of a second. So you compute that in a similar way. You plug in change in s, so it's s of 2.01 minus s of 2, again plugging in 2.01 here, then plugging in the 2 and subtracting that result. That gives us negative 0.2416 in the numerator, divided by the change in t, and remember, that's just a difference in the elapsed time, so that's 2.01 minus 2, so your denominator is 0.01, and when you divide those, you get an average velocity of negative 24.16 feet per second. So based on what we're seeing, it looks like as I get closer to 2, your elapsed time gets shorter and shorter. It looks like your instantaneous velocity is getting closer to negative 24 feet per second. And that's an estimate based on what you saw in part B of your computation. In order to confirm that, you would then check an elapsed time from 2 to 2.0001. So the closer you get to 2, the closer your computation will be to negative 24. Okay, so you might have some problems where you're doing several computations of slope in order to confirm what the estimate is. So that's your homework for this section. That's your lesson for this section. You should give the homework a try. Good luck.